Hey, howdy. Good morning, everyone. Looks like we're getting close to the end of the semester and senior design projects and final exams and final assignments and projects and all this good stuff. So anyway, hang in there. You're almost to the end. Also, of course, almost to the end of 410, 611. Okay, so just to get things, oh, by the way, another gorgeous morning this morning, right? I've lived in Texas almost 17 years, and I have never witnessed a spring like what we are experiencing this year. So it's a gorgeous spring, really great. Hope you all are getting a chance to enjoy it at some point during your busy schedules. Okay, so just quick announcement, of course, project number 4 is scheduled to be due on Tuesday at 11:59. So I'm sure that you've all hopefully shifted your attention to working on project 4 now that project 3, sorry about that, project 3 has been submitted. Also, of course, we have exam 2, which is coming up basically a week from today, right? And so remember that that's a take-home exam. And later today, hopefully later today, maybe tomorrow, I'll be posting a sample exam for y'all. And just like homework 4 was a preview of exam 1, sample exam 2 is a really, really good preview of your second exam, okay? And so make sure you get a chance to take a look at that sample exam. I'll have a review session. I'll try to do that in person, possibly on Wednesday, the reading day. It really just depends on some things that I have to clear off my schedule first. If I don't do it in person, I'll for sure be doing it by video, okay? But my goal is to try to have that in person, and I'll get all that scheduling stuff sorted out between now and when I actually post the sample exam, either today or tomorrow, okay? Yeah, and then that's it. Second exam is the end of the class. So basically, project 4 and exam 2 are going to rely very heavily on what we talk about, what we started talking about on Wednesday, what we'll talk about today, and what we'll talk about on Monday, and particularly for exam 2 on Tuesday, okay? And so it's basically just the spark ignition combustion and bringing all of this together at the end of the semester, okay? Okay, I think that's everything I wanted to announce. Any questions before we get rolling? We're all good? All right, very good. So we basically left off here on this slide, right, in the video lecture from Wednesday, where we started talking about this idea of a mass fraction burn curve, right? So if I just back up real quickly for a minute, right, we spent quite a bit of time basically walking ourselves through this spark ignition combustion process where we, of course, release a spark. That takes quite a bit of time to develop this flame kernel, but eventually the flame kernel establishes. That's sort of this frame C that you see in the image. And then once that flame kernel establishes, that's when you basically have a flame in the fuel air mixture. Then because of turbulent entrainment, that flame spreads very quickly throughout the whole mixture and then burns up the mixture as that turbulent flame entrains the mixture and then does that burn up. And that of course is frames D and E. And then finally things terminate and come to closure when you eventually get to frame F, okay? Okay, so, and then we talked a little bit about this idea of a mass fraction burn curve, right? That was this curve that we highlighted on Wednesday, where what we're doing with the mass fraction burn curve is we're basically calculating the rate at which the fuel is burning, right? And so, of course, before combustion begins, there's no fuel that's burned. And then as that combustion process begins, the burning rate steadily increases. We then get into this turbulent entrainment and rapid burnup period, which is essentially the steep portion of this mass fraction burn curve. And then once all of the fuel air mixture completes its burn up, we then start to slow down that burn rate, and eventually it levels off and ideally comes to 100% if we were to have 100% combustion efficiency in that combustion process, okay? Okay, so we're gonna spend a little more time today talking about this mass fraction burn curve, linking that to some controlled parameter such as, say, spark timing, and understanding how, for example, the maximum brake torque varies as a function of spark timing. We'll talk about what that means. And then we'll begin to start linking all of these things together in terms of how the initial temperature of the mixture affects the burn rate, the initial pressure, the compression ratio, where you locate the plug in the cylinder head, right? All of these things that we talked about all semester long is now going to integrate in these next few lectures where we bring this all together with the spark ignition combustion, okay? Okay, so with that, let me now stop sharing the screen and blank this out, okay? So essentially, whoopsie, there we go. Okay. So essentially this mass fraction burn curve, we were to draw this out, and I use different things to indicate mass fraction burn, right? I'll use MFB, mass fraction burn. I'll also use X sub B, okay, to essentially, mass fraction burned, okay, different ways of highlighting the burn rate of the fuel. And it's always plotted as a function of crank angle, right? The engine crank angle. And of course, as before, we kind of want to mark for ourselves where top dead center occurs. And of course, we're going to use 0 degrees to indicate top dead center, okay? Top dead center at the end of compression during the combustion process, okay? So everything to the left is going to be negative crank angle degrees, right? So if I just sort of say, oh, well, this is minus 45 degrees here, okay? That would be 45 degrees before top dead center, okay? And likewise, if I were to say that this is a positive 45 degrees, that would be 45 degrees after top dead center, okay? So everything to the left of 0 degrees or TDC is what we refer to as BTDC, before top dead center, and everything to the right is what we refer to as ATDC, or after top dead center, okay? Now, the other terminology that you need to be familiar with is the words retard and advance, okay? So if we are moving or shifting something further away from, basically, if we're shifting things to the left, then we refer to that as retard, regardless of where we are relative to TDC, okay? So if we're moving in this direction, this would be retarding something. Oh, I'm sorry, I'm saying this completely backwards. Just the opposite. This is advance. I'm so sorry. So if we're moving to the left, we're advancing things, right? Think of it in terms of the timing of the cycle. Must not have had enough coffee this morning. So basically, you're having things occur earlier in the cycle, right? If you're moving something to the left, that means that it's occurring earlier in the cycle. You're advancing the timing, okay? Consequently, if you move things to the right, if you're delaying when things happen, then you're retarding that event, okay? So if we move in this direction, then we're retarding something, okay? So we're going to come back to this again in just a little bit when we particularly look at the torque versus spark timing curve, where we'll do things like advance the spark or retard the spark, which is to say that we cause the spark to occur earlier in the cycle, or we cause the spark to occur later in the cycle, okay? So we'll come back to this terminology here in just a little bit, okay? Okay, so that's kind of how we read this mass fraction. I haven't drawn the mass fraction burn curve yet, by the way, and I'm not going to on this plot. I'll do that on another plot here on the other side of the board. But this is basically the general layout of how we, refer to all of this terminology on a something versus crank angle plot. And so this is also true, of course, if this were pressure that we were plotting here, or if it were maximum brake torque that we were plotting on this curve. And again, we'll talk about that as we go through today's discussion, okay? So let's actually draw what a mass fraction burn curve looks like. And so we write on here, of course, our TDC point, top dead center, okay? And I'm just going to draw the mass fraction burn curve, and then I'm going to highlight a few things on it that we use to define the characteristics of this mass fraction burn curve, okay? So the mass fraction burn curve basically looks something like this. Okay, and there's a few important features that we need to point out, okay? So number one, we need to point out where 10% mass fraction burn curve occurs. We need to point out where 50% mass fraction burn occurs. And we need to point out where 100% mass fraction burn occurs, okay? Okay, so let's go ahead and mark these points. So this would say be the crank angle location where 10% mass fraction burn occurs. And this would be the location where 50% mass fraction burn occurs. And then this would be the location, well, I didn't do that very good. Yeah, Okay, just a minute. It must be the end of the semester. I'll do it this way. This is, of course, where 100% mass fraction burned occurs, okay? And so then we'll also identify where 90% mass fraction burned occurs, and so we can go ahead and mark that there, okay? Okay, so, and then the final thing that we need to highlight is where spark timing occurs. And so we just, arbitrarily will say that our spark timing is at this location here. Theta spark is the crank angle location at which we release the spark in the fuel air mixture, okay? And so this is theta spark. So the spark releases at this point of the engine cycle. And then this would be theta 10%. And then this would be theta 50%. And then this would be theta 90%. Okay? Okay, so now we indicate these on the mass fraction burn curve, the 10%, 50%, and 90%, because we use two characteristics, sort of two time difference parameters to help us characterize this mass fraction burn curve, okay? The first is what we call the flame initiation period, okay? So the flame initiation period is the time between theta of 10% mass fraction burned and theta spark, okay? In other words, if you think back to those images that we were looking at, images A, B, and C, right? The flame kernel development period, that is the flame initiation period. We release the spark and we have to wait a certain amount of time in order for the energy of that spark to cause the chemistry of the fuel air mixture to take off in a suitably fast enough fashion where we actually develop our reactions into a flame, okay? And so we just more or less say that once we get to 10% mass fraction burned, the flame is basically established. And so we have our flame kernel and we're ready now to deploy into this rapid turbulent entrainment and burnup period, okay? And that's the second period, right? That's the second time characteristic that we define is what we call turbulent entrainment. Or the rapid burning period. And this is the time difference between 90% and 10% mass fraction burn, okay? So if I identify these two regions on our mass fraction burn curve, this region here is the flame initiation period. And rather than always write theta 10 minus theta spark, what I'll often do is define the flame initiation period as being delta theta D, okay? So that flame initiation period, I'll use delta theta D to indicate the flame initiation period. And the D stands for delay, if you're curious as to why I use D there. Basically, it's what we would oftentimes call the ignition delay, okay? It's the time that it takes between when we want combustion to begin and when we know combustion actually has begun, okay? The second period, of course, is the difference, the time difference between theta 10% and this theta 90%. And so this is our theta 90 minus theta 10. So this is the rapid burning period. And to indicate the rapid burning period, we use delta theta B. Okay, and of course the B stands for burning. Okay, so this delta, this theta 90 minus theta 10 is the rapid burning period, delta theta B. Okay. Okay, the last thing that we want to highlight before we start talking more about how something like spark timing affects this curve, which is then going to translate into affecting the pressure curve, which is then going to affect how much torque the engine can make, okay? Before we start getting into those details, the one thing that we want to note is this 50% mass fraction burn location. Okay, this theta 50%. We'll talk more about exactly where we want that theta 50% to be, but we achieve maximum brake torque, okay, when theta 50%, 50% of the fuel has burned somewhere between, say, 5 and 7 degrees after top dead center. Okay, so I'm just going to write that down, and we'll come back to that later on. Okay, so maximum brake torque, and we don't necessarily know what that means yet, but we'll come to it in just a moment. Maximum brake torque typically occurs when 50% of the mass fraction burned occurs by somewhere between 5 to 7 degrees after top dead center. Okay? In other words, 50% of the fuel has burned before that point, and the other 50% burns after that point. Okay? And again, just to kind of bring this back to things that we've talked about before, remember that if this were constant volume combustion, your mass fraction burn curve would look like a straight line until, you know, a flat line along the zero axis until you get to top dead center. And then it would instantly jump at top dead center up to 100%. And then it would continue as a flat line at 100% through the rest of the cycle, right? In other words, you burn all of your fuel instantly right at top dead center. Well, that's not physically possible, right? We can't physically do that just because of the necessary finite amount of time it takes for all of that chemistry to occur for the combustion process, right? And so what we have to do instead is we have to understand, okay, how can we optimize this burning rate of the combustion process such that we can achieve maximum torque or maximum efficiency, what have you, okay? And so if we take a look at this, and before we start talking about maximum brake torque, it's sort of the first thing that we're going to talk about in terms of what can be affected by something like spark timing, okay? Just imagine what would happen if you advance your spark timing, right? In other words, this is your nominal spark timing, and then you advance it. You move it so that it's earlier in the cycle, okay? You can sort of immediately think, well, what will probably happen is I'll just shift my entire curve this way, maybe by the same amount that I've advanced my timing, okay? Well, it's a good initial thought, but the issue is that these two characteristic times of the combustion process are affected by things that change when you change spark timing. So in other words, at the nominal spark timing, you have a certain flame initiation period, a certain delta theta D, a certain amount of time to go from spark to 10% mass fraction burn. When you advance your timing, for reasons which we'll talk about, that delta theta D gets longer. So you actually take more time to initiate that flame kernel when your spark timing occurs earlier, okay? Likewise, your rapid burning period, that delta theta B, again, for reasons which we'll talk about why, gets shorter. And so you do shift your curve forward, but the slopes of these various curves in the delta theta D and the delta theta B will change when you change that spark timing. And you have similar effects. They might be opposite in nature, but you have similar changes, right? In other words, delta theta D and delta theta B will change if you were to retard the spark timing from that nominal timing. Okay, and again, we're going to talk about why that is as we get through these next few classes. Okay, okay, so kind of keep that in mind. And now let's turn our attention to how this actually shows up in reality. Okay, and we'll look at something like the maximum brake torque versus spark timing. Okay, so to begin this discussion, let's just remind ourselves what the torque versus speed curve looks like, because I usually like to do this because otherwise we sometimes will get a little bit confused on what it is we're looking at when we look at torque versus spark timing, okay? So remember that torque versus speed, this is going way back to chapter 2 stuff, right? Project 2, and we basically have, you know, a curve that looks something like this, right? Remember, we spent a lot of time talking about this torque versus speed curve, okay? Okay, so you've got this image in your head. Now let's look at the torque versus spark timing curve, okay? And it's going to look very, very similar, but it's fundamentally different, okay? So this is our torque, and now we're going to have as our x-axis theta s, or theta spark, okay? And so this corresponds to our spark timing. Notice that the x-axis here is speed, engine speed. This is spark timing, okay? So the torque curve as a function of spark timing more or less looks very similar. Looks like this, okay? The difference is that this is the spark timing and it's referenced to top dead center, okay? And so top dead center might be somewhere over here. This might be 0 degrees, top dead center. In other words, this would be when the spark timing is top dead center, when I'm releasing the spark when the piston is at TDC, okay? And so all of these spark timings that I'm showing you here are all before top dead center, okay? So if I go in this direction, everything here is for spark timing that's before top dead center. And so this timing that we're looking at where we have the maximum torque, this might be 30 degrees before top dead center, right? Or if I use the same numbering scheme that I have here, negative 30 degrees after top dead center, right? So this minus 45 that you see here, this is the same as saying minus 45 degrees after top dead center, right? Or 45 degrees before top dead center, okay? And so this would be 30 degrees before top dead center, or you could also say that it's minus 30 degrees after top dead center, okay? So you have to be a little bit careful sometimes with these nomenclatures will oftentimes change without us necessarily realizing it. One easy way to think about it is that hardly ever your spark timing is going to occur after top dead center, okay? If you have your spark timing actually anywhere close to top dead center, you're going to run a severe risk of misfire in your engine because that flame initiation period takes so much time that by the time you develop the kernel and actually start to burn the fuel air mixture, you're literally degrees away from the exhaust valves opening, right? And so you have to have your spark timing occur well before top dead center in order for all of the magic to happen and have combustion begin where you need it to be such that you have a healthy, stable combustion process, okay? Okay, so this point here is when you release the spark about 30 degrees before top dead center. So this point might, for example, be 60 degrees before top dead center. And this point here might be 15 degrees. Who knows, right? This is all just kind of sketched out, okay? Okay, so this point where you achieve maximum torque, that has a special name to it, okay? It's what we call the MBT timing, or the maximum brake torque timing, okay? And so this is what we define as MBT, and MBT stands for maximum brake torque. And this timing, and so if this 30 degrees, for example, if this is our theta MBT, then theta MBT is the spark timing that gives us maximum brake torque, okay? So theta MBT is the spark timing that gives maximum brake torque. Okay? Okay, so these are all definitions at this point, right? So we have an idea of what maximum brake torque is. We have an idea of what maximum brake torque timing is, okay? Mass fraction burn curve, we know all of this stuff now, okay? So now the question becomes, and this is something that you're going to have to analyze in project number 4, okay? The question becomes, why does the torque behave the way that it does as spark timing changes, right? What's happening to the mixture, to the combustion process, to whatever, as we change spark timing that causes the torque to decrease if we advance the timing too soon, right? Or if we retard the timing too late, right? Okay, so to answer that question, what we're going to do is we're going to bounce back to the slides for a quick minute. and then we're going to kind of draw out a visual so that you can sort of see thermodynamically how this makes sense, okay? So let me just lower the screen real quickly, and we'll go back to our sharing of the screen. Okay, and so this is the slide number 6 is basically that figure that you see on the right-hand side, right? Relative torque as a function of spark advance, okay? That's showing you the torque as you change spark timing, okay? And then you can see, of course, that it's highlighting for you where MBT occurs, maximum brake torque, okay? Now, there's one really important thing to note on this diagram of torque versus spark advance, okay? The x-axis is in the reverse direction than what I drew on the board, okay? So and again, this is where you're going to see differences in convention about how different people, and that's why I draw it intentionally the way that I do it on the board, because you have different people that do different conventions, right? You know, this is one of the joys of engineering, is that people speak in different languages and look at things differently, okay? And so this torque versus spark advance, basically this 10 degrees is 10 degrees after, before top dead center, okay? The 20 degrees is 20 degrees before top dead center, 30 degrees is 30 degrees before top dead center, so on and so forth, right? Well, this is just the opposite as what we drew on the board, right? Remember that we were saying that things that go in this direction from the left to right is going to, you know, retarding in the cycle, going later in the cycle, okay? It's just the opposite in this figure, whereas you go from left to right, then you are advancing the timing in the cycle, okay? So just be real careful when you look at torque versus timing diagrams and things of that nature to really understand exactly where things, you know, how they're orienting their axes and providing this information, okay? But the concepts are still there, right? In terms of the fact that the torque, you know, has a maximum brake torque timing, right? And so that maximum brake torque timing is occurring at about 33 degrees before top dead center, okay? So the spark is releasing about 33 degrees before top dead center, and then you have this flame initiation period and then the rapid burning period. And if you were to look at the mass fraction burn curve for that 33 degrees before top dead center spark timing, you would see that the 50% burn point occurs around 5, 6, 7 degrees after top dead center, right? And again, we'll see that here in just a little bit. But before we do that, now let's take a look at how the spark timing is changing the pressure behavior inside the cylinder. And again, that's going to translate to why the torque is changing the way that it does as we change spark advance, okay? So notice that as we advance the timing, right? So this is a spark advance of 50 degrees before top dead center. This, so that's this pressure profile that you see here. This pressure profile that you see here is for the spark advance of 30 degrees before top dead center, right? So that's sort of close to the MBT point where you have maximum brake torque. And then your later phased timing, the retarded timing, is 10 degrees before top dead center, okay? So let's first focus on the 10 degrees before top dead center spark advance, because that one's a little bit easier to understand what's going on, okay? Remember in Wednesday's class, we talked about the motoring curve, right? Where you basically compress your mixture, you reach top dead center, you don't do anything with the fuel air mixture, right? You don't ignite it. And so the piston compresses the mixture, reaches top dead center, and then expands the mixture. And you get this nice smooth curve, which we call the motoring curve, okay? Well, that's sort of what you're seeing here with this 10-degree spark timing curve, right? You're seeing the compression curve, you reach top dead center, and because combustion is starting so late, you actually begin to expand the mixture before combustion has a chance to really take off and release the chemical energy and cause a rise in pressure in the cylinder, right? And so the expansion of the piston causes the pressure to drop a little bit, but then finally combustion catches on and takes off and causes that secondary rise in pressure, this rise in pressure that you see here, where then finally you get peak pressure due to combustion, and then the combustion process ends and begins to expand as the piston expands the mixture, okay? Of course, you compare that to 30 degrees before top dead center, right? So Now our spark timing is, roughly here at 30 degrees before top dead center. You undergo compression, you have spark advance here, and then eventually combustion begins at such a point that you begin to see the departure of the pressure curve from the motoring curve, right? And so this small departure that you see here, as combustion is beginning to raise pressure in the cylinder, right? And then that combustion process continues as the piston approaches top dead center. Combustion is still occurring, even though we're after top dead center. Here's TDC right here, right? So pressure continues to rise, even as the piston is now expanding the volume. So combustion is burning at such a rate that it still causes the pressure to rise as the piston is expanding the volume. And then eventually you reach peak pressure, right? And the combustion process begins to die down, and the piston expansion now overtakes the rate of combustion, and eventually combustion ends and you begin to expand the mixture through the expansion stroke, okay? And then finally, if you have a very advanced timing, like 50 degrees before TDC, you of course are starting your combustion very early. You have a very early rise in pressure, a much higher rise in pressure, right? It gets to much, much higher pressures. You reach peak very close to top dead center, and basically combustion quickly terminates, and then you go through the expansion process, okay? Okay, so let's link these two together, maximum brake torque with the pressure behavior that you see in your cylinder, okay? And so first of all, you want to remember that what really matters, what torque is related to, right? Think back to chapter 2 stuff, right? What torque is related to is how much the net work of the cycle is, okay? The net work of the cycle. And so if your torque is decreasing, that means that the net work is decreasing, okay? So you might look at this pressure curve, for example, right? And you'll, if you just sort of think, okay, well, torque is related to net work, and net work is the area under my PV curve. And so if I increase my pressure, that's going to give me more work on my PV diagram, right? But that's clearly not what's happening here. At 50 degrees before top dead center, notice that the torque curve is beginning to drop off. 50 degrees is perhaps right here. That torque curve is dropping off. And so you get a much lower torque, even with much higher pressures in the cylinder. And it's all because those rises in pressures are not occurring at the right timing, right? They needed to occur later in order to affect a higher work out of the higher pressures, okay? So even though the pressure profile for 30 degrees is much lower peak pressures, it's timed correctly in the cycle such that you are maximizing the work under your PV diagram, okay? So let's kind of draw what that means on the board. Okay. And we'll do a very simple, sort of almost like a thought experiment to help us understand what's happening here in terms of this phasing and how we classify the fact that we're producing less work, less torque at these different spark times, okay? And what I'm going to do is I'm going to rely on our good friend constant volume combustion, right? Even though of course, we recognize that we don't have constant volume combustion inside the cylinder, this does a very nice way of explaining what's happening if we have ignition occur too early or ignition occur too late, okay? So we have our PV diagram. And let's first of all suppose that we were to draw the maximum brake torque, right? And so we have, again, we're going between our volume at top dead center and our volume at bottom dead center, right? Say this is our initial pressure here. And so we're going to compress the mixture all the way up to top dead center, okay? And then, we have our combustion process timed perfectly so that combustion occurs right at top dead center, releases all the fuel energy right at top dead center. So we raise our pressure due to combustion, right? And then, of course, we undergo our expansion process back down to bottom dead center, right? We've drawn this 100 times. You know this really well. Well, what happens if spark timing occurs too early, right? So this is the spark timing that gives us maximum brake torque from the engine. Well, what if the spark timing occurs too early, right? We don't ignite the mixture right at top dead center Instead, we ignite it a little bit early of top dead center, right? Well, our PV diagram might look something like this. And again, this is all highly idealized, right? But our PV diagram might look like this, right? Where we get somewhere early of top dead center, okay? And then just for the sake of easily drawing this, we then have combustion that occurs instantly at that volume. But now the piston still has to go from this volume to top dead center, right? We can't change the kinematics of the piston cylinder arrangement. And so it ends up being compressed to the point of top dead center. We reach top dead center. The fuel and air are already combusted. We already have burned products of combustion. And so we just ride along that curve right on back until we eventually get to bottom dead center, okay? And so you can see right away that your lost work, right? Remember that work is the area under the curve, right? Work is the integral of the PDV, right? Which is to say that it's the area under the curve, okay? And what we've done is we've decreased the area by having combustion occur too soon, okay? And we essentially have lost this PDV, right? We've lost that area by having the combustion process take place too soon, okay? And so this is our lost work opportunity for too early of combustion. Okay? So that's what happens when we have spark advance occur too soon. Okay? Even though, of course, if you look at the pressure diagram in the slides, we go to much higher pressures. Even with those higher pressures, you're still losing that change in volume, right? So you might gain some area by having a higher pressure on the expansion side, but because you lose this portion here, you have this lost work as a result of combustion occurring too soon, okay? So what happens if timing is too late, right? What happens if we ignite the mixture later than this maximum brake torque timing? Well, we can draw that as well. And so I'll do that on a new diagram just so that it's clear. And so again, we have our PV diagram. And we're going between top dead center and bottom dead center. Okay, and let's say we're starting at this point here. We have our combustion process. This is the MBT timing diagram, right? Just like what we drew before. And now, if we start combustion too late, right, then again, we'll undergo compression. But because we're starting timing after our ideal timing, we go all the way up to compression, hit top dead center, and begin to expand. So we're riding right back along that curve, and then have ignition. So we have our rise in pressure due to combustion, but of course it's occurring as the piston is moving from top dead center to bottom dead center. We have the rise in pressure, and then we have our expansion, right? And so again, you can see right away that what happens is we have this lost work opportunity as a result of the later phased combustion timing, the retarded combustion timing. And so this is our lost work opportunity for combustion occurring too late. Okay. Okay, and again, this is a simple diagram, right? Because if we look at the pressure versus crank angle diagram in our slides, we are going to much higher pressures in our cylinder when we advance the timing, right? In other words, if we have too early of timing, we end up going to a much higher pressure and expanding that. And so this is sort of a work that gets gained, right? This is the work gain. And so if you take a look at that torque versus spark timing curve, you'll notice that the decrease in torque on the retarded side is steeper than the decrease in torque on the advanced side, right? So it might look something like the following. So if we have torque versus spark timing, and say this is our theta MBT. And again, if we go in this direction, we're advancing the timing. And if we go in this direction, we're retarding the timing. So again, remember, I'm drawing this opposite. I've reversed the x direction compared to what, relative to what's in your notes, okay? And so essentially what we see is that this maximum brake torque curve might look something like this, where we have a subtle rise in torque as we reach theta MBT, but then a rather drastic drop in torque as we retard the timing, okay? And so the way that we describe this is that the loss in torque with a retard in timing is due to what we call expansion losses. In other words, we're not taking full advantage of the expansion stroke. We're curtailing ourselves on how effectively we're using the expansion stroke of the piston cylinder arrangement, okay? And so this drop off in torque is because of this lost work opportunity that we have here, okay? If we had, on the advanced side, the reason why it's not quite as steep is that, yes, we have a similar type of an expansion loss, right? In other words, it's a sort of a pseudo expansion loss in the sense that we ignite so early that we burn everything before we can have the chance to utilize the expansion stroke here, right? In other words, we compress those burned gases up to top dead center, but then, you know, if there's no heat transfer, and I'm going to talk about that in just a moment, then this curve will follow along the exact same path. And so that work that went into compression is balanced by the work that you get from expansion, okay? And so there's again, it's sort of this pseudo expansion loss by having the timing occur too soon, okay? So our losses on this side are basically composed of two parts, okay? So we have a loss in torque due to, number one, expansion loss with combustion occurring too soon, which is mitigated, which you don't get on the spark timing retard side, which is mitigated by much higher pressures relative to the retarded spark timings, okay? But there's a second effect that causes you to lose torque if you have too advanced of a timing, and it's related to that higher pressure, right? So if you have higher pressures in the cylinder, that means that your mixture is going to be at higher temperatures, right? PV equals MRT. And so if pressure is higher, your temperature is going to be higher. And the higher your mixture temperatures, the higher your heat losses, the higher your heat transfer rates, okay? And so you also have a loss in torque on the advanced side due to higher heat losses resulting from higher pressures. And the higher pressures translate into higher mixture temperatures. And of course, the higher mixture temperatures leads to higher heat transfer, et cetera, et cetera. You get it all, okay? Okay, so this is how you analyze the torque versus spark timing curve, right? Which is, of course, a major feature of project number 4, okay? And so at this point, you're able to address a lot of what it is you need to describe and analyze in your project number 4, okay? What we haven't talked about, and what we'll need to continue talking about on Monday, is the relationship between this spark timing and its effect on the burn rate itself that is causing these changes to pressure that's leading to this behavior in the engine torque, okay? And so that's where we can now start to I'll just briefly introduce you to it, and then we'll pick this up again on Monday. But this is where we now start to bring in discussions about this flame initiation period and the rapid burning period, okay? So the closing thoughts that I'll leave you with are the following. The burn rate in a mixture is affected by the spark timing in the ways that delta theta D, the flame initiation period, and delta theta B are affected by spark timing. In other words, the spark timing is ultimately influencing delta theta D and delta theta B, and this is what's causing the difference to the burn rate, and that's what's causing the difference to the pressures, and that's what's affecting the maximum brake torque, okay? And so delta theta D, the flame initiation period, and again, we're going to talk about this more on Monday, but just to whet your appetite, this flame initiation period, delta theta D, is a function of what we call the laminar flame speed. So this delta theta D is a function of laminar flame speed, S sub L, okay? So S sub L is the laminar flame speed. Okay. And this rapid burning period, delta theta B, is at a 10,000 foot view, a function of what we call the entrainment rate. And again, we're going to describe all of this on Monday. So it's a function of the entrainment rate and the burn-up rate. And these two things, the entrainment rate and the burn-up rate, are functions of a lot of other stuff, okay? And again, we'll talk more about that on Monday, okay? And the laminar flame speed is also a function of a lot of stuff, including temperature, pressure, and mixture stoichiometry, like how lean, rich, or stoichiometric the mixture is, okay? So we'll pick this up on Monday. I just wanted to leave you with this before we broke for the weekend. Any questions before we break? All right, very good. Thank you all for coming to class. I wish you all a great weekend, and we'll see you on Monday.